Hi everyone, my name is Christopher Lutat and I'm the product manager for the open-appsec open source solution at Check Point Software Technologies. In this video I will explain you in depth how open-appsec's contextual machine learning engine is working so that it can protect web applications and web APIs preemptively and automatically, not just against OS top 10 attacks, but also against real zero-day attacks without any signatures required at all. I will use within this video the well-known Log4j vulnerability series as some specific examples which recently caused a lot of harm to businesses worldwide to show the specific inner mechanics of the contextual machine learning engine of open-appsec. We will start with a quick overview of the open-appsec project in general, before then looking at the specific challenges that arise from the use of static signatures in traditional, still pretty common WAF solutions. Then we will have a look at the Log4j zero-day vulnerability series. There was a total of 3 very famous CVEs within a very short time, so we will dive into this a little bit, before then checking if a signature-less machine learning-based approach might be way better suited to actually provide preemptive protection against 0 days. We will then look at specific zero-day attack examples, again based on the Log4j attack series, and see what happens in the contextual machine learning engine of open-appsec when those are fed as requests into the engine to be analyzed, and how the actual verdict is being taken by the open-appsec engine. Then I will show a quick demonstration in open-appsec, firing a real attack and seeing what happens, like successful example, and also one where it gets prevented by the open-appsec machine learning. And then I will conclude this video with some final takeaways. So let's start by having a look at the open-appsec project. First, let's see what's the difference between legacy AppSec solution and modern AppSec solution. The thing is that legacy security just technically is not able to defend modern applications against specifically 0 days at all. Why? Because it's mostly a 20-year-old technology. It's in many cases still signature-based even today. Which means in most cases as well that it's not looking at the context of the specific request. And this again leads to the fact that there is usually a lot of false positives. And those again cause a significant administrative overhead, because if you have false positives, then typically what you need to do is you need to do specific, create specific exceptions for the false positives so that they don't impact the actual production traffic and potentially harm your businesses. So a modern application security solution on the other side, that's first of all should be built for modern web applications and platforms. That means, for example, also support for, I don't know, Docker and Kubernetes and all the modern platforms that we see these days in the public cloud and also locally. It should support the option to have a local management and also a central management. It should involve much more or work differently than just based on static signatures, by doing a multidimensional security analysis and take the context into account, like the specific user or learning about what's happening typically on this website and doing some stuff of like baselining and so on. It should be GitOps CD process ready in the way that everything should be configurable also via a declarative policy, so that you can have the full configuration, deployment as well as configuration, ideally just in your Git repo, and then use some GitOps process to get it deployed as well as configured with all the benefits of using GitOps CD, like having proper versioning and management for your changes and so on. Then it's important that a modern AppSec solution also allows precise prevention without relying on signature updates at all. And we will see later how this is technically possible. And it should also allow or provide a fully automated solution which requires zero policy administration effort to get you protected against all kind of modern attacks, including 0 days. So what is openappsec in short? It's an open source solution, as the name suggests. It's a WAF style solution. It's under Apache 2.0 license. You find the repository in github.com/openappsec. It's completely based on machine learning to provide you preemptive threat prevention for web applications and APIs. And it can protect your applications and APIs against the typical OS top 10 attacks, but not only those, even more. And it also includes protection against real 0-day attacks like Log4j, Spring4Shell, Text4Shell, just to mention some examples where openappsec was the only known solution that without any update requirement or signature update requirement was able to prevent all of those attacks from day 0. So openappsec therefore is not relying on signatures. We will learn later why this would anyway be contradictory to providing 0-day protection, and therefore also not relying on signature updates, of course, and only this is what allows it to provide true 0-day protection. It's available for all relevant modern platforms, so that includes Linux, Kubernetes, as well as Docker or containerized platforms in general. It's made for DevOps and DevSecOps team usage and processes in the way that besides having a nice central management option using a web UI, it also allows you to have all the configuration managed in declarative form so that you can store it within your Git repo, for example, that you use in terms of GitOps CD processes. The openappsec solution is available as a free community edition, and if you require support for your enterprise, for example, then there's also a premium solution, a premium tier available, and an enterprise edition that provides some additional features and also provide you technical support direct channels to us. While it's important to say that the free community edition already provides you the same core security engine capabilities as the premium and the enterprise edition. And yeah, so in terms of prevention, you get the same core technology already with the free community edition. And you also get access to the web UI, also included in the free community edition already, to have like a nice UI experience to manage your stuff or do reporting, check out security events, and more. In terms of platform support and integrations, as I said before, we support Kubernetes, Linux, and Docker on the platform side. Then the openappsec solution integrates with Nginx and Kong at the moment. We plan to add integration into Envoy and emissary ingress soon as well. So work for this is already in progress. In addition to this, we also recently announced a partnership with Crosssite, where we allow you to consume threat intelligence that is provided by Crosssite and also report the threat intelligence based on openappsec's advanced detection and prevention mechanisms based on the contextual machine learning engine. Report this intelligence back to the Crosssite community threat intelligence so that other users of Crosssite can benefit of this. So we are really looking at living the open source thought here and trying to evolve our ecosystem with integrations and providing you more and more options to actually protect your environments with openappsec. And the core is based on us integrating with a reverse proxy solution, and this is what Nginx and Kong are at the moment, where we'll also add Envoy and emissary ingress. So, as said before, openappsec is the only real preemptive WAF solution in the market. So the core of this is our contextual machine learning engine, and the actual proof of this was already seen over time when you just look at the most famous attacks that were out in the wild and everywhere covered in the press. So the open-appsec contextual machine learning engine was able to prevent attacks on all the three famous Log4j vulnerabilities, which each got their own CVE number in late 2021. Then in March 2022, there was this famous Spring for Shell vulnerability. Then there was in November the Text for Shell vulnerability, and in end of 2022, the Clarity Team 82 released a new generic bypass technique, SQL injection style for all industry-leading WAFs, with one exception, which was open-appsec, where you can also read on their blog that actually they mentioned that there was only one solution which couldn't be evaded by their new bypass technique, which is pretty good point for, again, the effectivity of our contextual machine learning engine. So let's have a look why using static signatures in WAF solutions, or specifically relying on static signatures alone in WAF solutions, might not be a good idea. The thing with signatures in WAF solution, or signatures in general, first of all, is that by design, signatures can only be available after new attacks were published, because you need to create a signature somewhat for specific attacks, attack types, and so on. That means that by design, a solution, a WAF solution that relies solely on signatures, does not offer preemptive zero-day prevention. In addition, the situation is that vulnerabilities, of course, usually exist long time already before a CVE is actually published, which leads to the fact that for the time of the so-called vulnerability window, which starts when a vulnerability is introduced and someone might already exploit it, as you can see here in this phase, where some hackers might already have an exploit. So then from this point on, you are already vulnerable. Your systems are already vulnerable if there's a vulnerability in a certain module or package or solution or whatever. And then at some point, a CVE is created, but just because the CVE is created doesn't mean that the signatures are available right away. So there's the point where CVE is created, and then based on the CVE, signatures are created. And then while the signatures are being created, even before they are created, of course, many more hackers are now getting information about this and start to look at additional exploits and to look how they can take benefit of this, the information in the CV. So there might be more people actually trying to use exploits and have access to some exploits already. And then at some point, the exploit code itself is actually published so that everybody can use it. And when this is the case, then typically short after, all the typical WAF vendors also release their signatures based on what's known about the well-known exploits for the vulnerability that was released in the CVE. But in reality, it's even worse, because similar to what we see in the COVID scenario with the SARS-CoV-2 virus, which often created mutations over time. So there is not just one virus strain, but many different ones. Also in IT, we see that one vulnerability often leads to new mutated vulnerabilities. So in addition to the flow we saw before, where you have a vulnerability and then at some point there's a CVE and then there's an exploit code released and then there's a signature, there might soon after be another exploit for the same CVE, which requires like adaption or a new signature again for that exploit type. And then while this first of all makes your environment again vulnerable for a short time, as you see here by the reddish color on this arrow. But then again, in parallel, people are looking, because of the first CVE, more and more into perhaps other vulnerabilities in the same module. Let's look at, for example, the Log4j functionality. And they often succeed and find another CVE in the same context, in the same solution, in the same module or library or whatever. And then the whole story begins from the beginning, and another vulnerability window opens again, waiting for CVE release, exploit code to be released, and finally a signature being available, which obviously also only protects you once you then get to the point where you roll it out widely in your company. So is there something like a one size fits all for signatures? Can you have one signature that just covers it all? Let's look again at the COVID-19 testing example. So with testing for infection with COVID-19, if you have a false positive, that obviously gives you a lot of frustration, stress, impact on the family, impact on your job, lots of time lost because you might need to stay at home, and all of this just because of a false positive. So that's definitely not a good thing. But also, if you get a false negative, that's really, really problematic, because a false negative in COVID-19 testing means that there is obviously a risk of infecting and harming others, because you don't know that you are infected, and your own symptoms might be prolonged because you don't know you're sick yet, and instead of relaxing at home and getting better, you might just continue to go to work and do sports and stuff that actually can pose a health risk to you. So when we take that example and look at AppSec signatures, there, first of all, you can have less specific signatures. If you have less specific signatures, it means you get higher security, but also you get more false positives potentially, because they just like take more requests and consider them malicious. If you have more specific signatures, then this leads to lower security with the potential of creating false negatives, but also reduces less false positives. So none of this is perfect, and it's always like a trade-off. And in terms of AppSec signatures, false positives can actually block customers' access and impact reputation, financials, and more, while false negatives, on the other hand, pose important security risks and can cause reputation damage, data loss, and more to your enterprise, because obviously if you block valid usage and valid users from accessing your services, your website, then this is not good and definitely causes harm. So therefore, obviously, detection accuracy is very, very critical for a good WAF solution. So looking at this, we are actually in need of a new approach. The new approach for WAF implementation should protect against mutations as well. So as we saw in the example where I showed the vulnerability window, but it also should address the false negative, false positive trade-off challenge that I have explained before. And while saying this, let me also already state that, of course, signatures by itself are not bad or harmful. They are still useful. So doing signatures and putting expert research effort in looking for signatures and so on is still relevant, of course. But the purpose of signatures, where they are actually used, that is what might change in the future. So let's now have a look at the recent Log4 Shell and Log4j attack series, and check the timeline and the different CVEs and the resulting challenges. Couple words first about what Log4j actually is. So Log4j is a widely used open source framework, and it's used for logging application messages in Java, and specifically this is kind of the de facto standard today, used in many deployments worldwide in enterprises of all kinds. And Log4Shell was basically the name given to the first critical Log4j vulnerability, which was found by Chen Zhaojun, working at Alibaba's cloud security team in November 2021. As a result of this, a CVE was created in December, so a couple of weeks later, and it was immediately assigned CVSS severity score of 10, which means it's an absolutely critical vulnerability. But it's also important to say that this one actually went unnoticed already since 2013, and so you can see how long the vulnerability actually was. So it took many, many years that there was a critical vulnerability, and only then in 2021, end of 21, someone found it, and a patch for the log4j framework was actually available 12 days later after the discovery, adding up to the vulnerability window. But in comparison to the long time this existed, this was only like extending it slightly. But that wasn't it, because more related log4j vulnerabilities followed very soon after. So let's dive into this a bit more and also check the technical side of this. So this first one, the log4shell vulnerability, this was based on usage of the so-called Java naming and directory interface, in short JNDI, which is the functionality that allows distributed Java applications to look up services in an abstract, resource-independent way. So by using this, in certain log4j versions, it was possible to include lookup metadata that technically ordered log4j, the log4j module, to connect using the JNDI protocol to specific servers. And the important thing to notice here is that the protocols that could be used here and the resolvable names were not restricted at all. So, for example, you could connect to an LDAP server and send something there, and then it returns something. But what it returns and what you send there was completely unrestricted in the log4j version, in the vulnerable version at that time. So this made an exploit possible because some protocols were unsafe, and therefore there were ways to do remote code execution based on this. I will also show this in a quick live demo later to show a very specific detailed example. Meanwhile, there's patches that can disable these features by default, just to mention this. So in this log4shell example, the typical exploit string looked like this in the beginning. So you had like $curly brace JNDI, then a specific protocol, which could be, for example, LDAP, and then the server that the connection should go to. And in the first samples, always LDAP was used. So the first signatures we saw being used by WAF vendors were actually looking for the string $curly brace JNDI : LDAP. But it didn't stop there, and soon new samples appeared, and then they switched to using different protocols. So they used the secure version of LDAP, LDAP-S, and RMI, DNS, IOP, HTTP, so many more protocol variations. And this led again to many more signatures being created, where for each of them, of course, like once the signature is there, it takes you also time to actually update your solution, or it might be done automatically on a nightly basis. But like every single new sample and exploit causes another vulnerability window, as I've shown in the beginning, that needs to be closed again. And on the same side, at the same time, the number of evasions also grew continuously. So, for example, the bad guys then started trying to bypass string matching detection by introducing some kind of obfuscation to the exploit string. So here we can see an example where they used a lower command, which puts the character L, which is already a lowercase character, of course, but puts it again in lowercase, resulting in the exact same character. But this is some easy way of doing an obfuscation, for example, so that the signature string like this one wouldn't work anymore. And there's other obfuscations which look even more complex, where you introduce a lot of characters that actually don't do anything, or functions that reside in the same thing that you actually enter into the function, to avoid simple signature-based approaches. But the story continues here. So right after the initial CVE, just a couple days later, there was already the next CVE published. And this time it was like a denial of service style attack that allowed execution of infinite loops on the victim server. So the CVSS risk score for this new CVE was raised from initial 3.7 to 9.0, turning it again into a critical vulnerability, because someone found out that using this also remote code execution was found to be possible by using this exploit. So in this case, the usage of pattern layouts was possible in Log4j, and developers could use this feature specifically to extend log messages with specific metadata, like, for example, adding a date or time to a specific log. And also they can customize the log info using so-called thread context objects that refer to context lookups, so that you can see in this example the dollar curly brace CTX to specify a context. And based on this, it was possible to actually create like an infinite Java loop. So you have the context actually refer to itself. So whenever you see the context, it tries to look up the context, which is itself, and then it's triggering another lookup of the context. And obviously, this is a nice way of doing a denial of service. But again, it didn't stop there, and still in December 2021, there was the next CVE for Log4j. So this time, December 18th, again, a pretty high CVSS risk score of 7.5. It was slightly reduced later on. And this new attack was again a way to cause denial of service on the target system that the bad guys attack here. And this time it was actually triggering an infinite recursion by using native Java constructs. So you see this pattern example that is shown here. And as you can see, this again looks different from the ones before, that where mainly the signatures were based on JNDI and the protocol, or on the CTX reference as the string to identify that this is an attack. And this time, none of this exists here. And there's more to it, and more vulnerable, different exploits for each of the CVEs, but I think this should be good enough at this point to give you an idea of the complexity and why signatures are just not good enough to prevent these, because they are by design always too late. So in the first month's timeline, we saw like on December 9th, the initial log4j being published, then there was a patched version of log4j, then at the 14th of December, the next one was published, next CVE, and again there was a new version of log4j. You were like in a continuous loop of doing patching and installing signatures to protect against them and so on. On December 17th, there was the third one published, and again there was another version of log4j that was recommended to address the security vulnerability. So if we look at this example, or all those examples to be more exact, then it shows like patching the vulnerable systems needs to be done over and over again once new patches are available. That requires high effort. Signature-based solution only protect after the CVEs and after subsequent exploit release and signature release, when you then finally install the signatures in your system. So again, like every time your web services are left unprotected for hours to days, and even way longer, because obviously the exploits in most cases existed already for months or years from the date of their initial introduction. So no one knows if someone already exploited it in the past, because no one knew that there is this vulnerability. But technically the real vulnerability window can be as long as multiple years in many cases. The question is, can machine learning actually solve these challenges? So is machine learning technology able to actually provide real preemptive protection against zero-day attacks that solves the challenge that we've seen with regards to the vulnerability window leaving you unprotected for some time? Can it function completely independent of signature updates, because signatures obviously are not good enough? And can it, on the other side, also address the trade-off challenge between like more specific, less specific? So somehow address the challenge with the false positives that we see with all the signature-based solutions. So now let's look at how open-appsec's contextual machine learning engine can provide a new security layer for delivering you actual preemptive web application and web API protection. The contextual machine learning engine in open-appsec is based on a two-stage enforcement model, or two phases. So in the first phase, we have the attack indicator observation phase. So here we search for short patterns of exploiting vulnerabilities. And these short patterns, which we call indicators, so an indicator can be as short as just like one character or two characters in the extreme cases. They have been generated based on evaluating millions and millions of malicious and benign HTTP requests based on a supervised machine learning model, so that for, first of all, to come up with the specific indicators, and for each and every indicator to get like a score that represents the likelihood of this indicator to be actually part of a malicious request of an exploit or not. So then after in phase one, we search for those indicators in the actual HTTP request. Then in phase two, the contextual machine learning engine goes one step further, because just the fact that you have like one or two characters in phase one is obviously not good enough to determine that this is really like a malicious request. And therefore in phase two, the machine learning engine is putting everything in the context. So based on the initial finding of phase one that it might be a malicious request, because there's some indication about it based on some indicators we found, we then look at the full application structure and how users actually interact with content. So we look at how often specific requests happen on specific URLs in specific, how often specific values that come along with the HTTP request contain specific content and specific indicators, what the reputation is of the user, so how did the user behave so far when accessing the website. And the evaluation of the incoming HTTP request in this case is also based on a machine learning model, but in this case like a non-supervised machine learning model, which is built in real time in the protected environment and is very specific to the actual traffic patterns going into your specific environment that you protect, in comparison to the phase one machine learning model, which was built offline and is a supervised machine learning model. So how do those indicators look specifically? Let's go into this a little bit more deep. Instead of traditionally using long and rigid signatures, so you already understood why this is not a good idea, I assume, we use very small indicators. And if we look at this example for a very typical SQL injection attack, then we, based on this example, open-appsec's contextual machine learning engine would identify a long variety of indicators. So for example, just the double quote is an indicator by itself, but like just having a double quote, of course, it's quite often used maybe in attacks, but by itself it doesn't have a strong indication that it's really an attack. Then an equal sign, for example, is not so commonly used in values and HTTP requests and so on. So that has its own score, which is like fairly high, and then there's like a single quote and two dashes. So all of these are individual indicators for which for each and every one of those we know the likelihood of this being part of a malicious attack. And also we have what we call combined indicators. So while like the single apostrophe might have a score of 0.01 of being part of a malicious attack, if it's the apostrophe in combination with another indicator, which is two dashes, then it gets a different score, because like in that specific combination, it might be like much more likely to be part of an actual attack. So, and based on all those indicators, that's happening again in the phase one of our engine. As a result, we can calculate a total score, in this case 8.6, as the total result for the analysis of this request in phase one. So this already allows us to have a very effective determination for an initial decision if we want to further analyze this and if it's like looks more or less suspicious, um, to then decide that this needs to be handed over to our phase 2 for deeper analysis. So here I'm showing you just a list of specific other payloads, malicious payloads, and how they are analyzed in phase 1, and also showing you a list of the actual indicators that are found by the contextual machine learning engine um, based on those specific text strings that you see here on the malicious payloads, and also the score. So I'm obviously not going through this like one by one, but just to give you an idea that, for example, in this example where someone tries to download like a dump SQL TGZ archive from a system, hoping to gain interesting information from this, like we would in stage 1 identify .tgz, for example, as an indicator with a certain score, and dump SQL as an indicator with a certain score, and much more. And in the end, we get to a score of 6.9, which means it's pretty likely that this could be an attack. But we are not stopping there, but actually hand it over then to stage 2. So we just described or looked at the phase 1 indicators detector. And if there's at least a single indicator identified here, if there's no indicator, then of course traffic is okay and it can just pass. That's the case for 95 to 97% of all the requests that we typically see. But if there's some indication here in that phase already, then we consider it potentially malicious and consider it suspicious, and we hand it over to further analysis in our advanced analysis engine where we do the contextual machine learning analysis. So here we are looking at more different dimensions like user reputation, payload score, URL score, and parameter score. So as a result, in phase 2, either it's like confirmed that the initial suspicion from phase 1 is actually true and the request has a high risk and therefore is to be blocked, or it's returned, it's not returned, it's forwarded and just passed based on a determination that although there's some initial indication that it might be an attack, looking at the additional context might make us know that this is not really malicious and it's actually benign traffic, and so we can pass it. So in phase 2, as I said, we have the different contexts. So what we look at here actually, first of all, is the user behavior. So we know if a specific user in the past already built up some kind of reputation with our system. So if this user never did anything which was determined to be suspicious so far, then this specific user, which could be like a source IP of the user, of course, or the user identification based on some header or whatever, then we can evaluate this and consider it in our final verdict about this being a malicious activity or not. So if we saw a user that already did very suspicious stuff all the time, then it again adds to the confidence level of something being an attack, of course, and the other way around, we might reduce the confidence level. Then we also look at the specific transaction. So this is basically the result of the phase 1 verdict, which we've seen before, where you see the individual indicator scoring and the total score, and that's handed over as well to the phase 2 analysis here. So that's the transaction dimension, let's say, or context. Then we look at the actual application context. So is, for example, the indicators that we see, are they something that we typically see on that specific parameter, on that specific URL, and we also do this on specific value perspective, but we also look at the full crowd behavior for what we see on the whole website, on the whole URL, and so on. So we do a lot of baselining and checking what's the normal behavior. and what stands out as untypical suspicious behavior here, before then in the end we do the final verdict. And last but not least, we also have a way that you can configure so-called trusted users and tell to the system that traffic originating from a certain group of users is actually to be considered benign, because you know those users, so that you can actually accelerate the machine learning, and whatever the machine learning engine sees from those users adds up to normal usage consideration or normal usage baselining from the perspective of the machine learning engine. So, and taking all those different contexts together, so the reputation score, the payload score originating from phase one, the URL score, and also the individual parameter scoring, this allows the engine, as a result of phase two, again, to come up with a combined total score. And depending on that combined total score, that says like how suspicious this request is to be actually an attack, and strongly reduce its false positives at this stage by looking at all those additional contexts. Then based on that final score, the decision is made if traffic is supposed to be prevented, or if the request can actually just be passed because they are considered to be benign. So in the phase two, the target is to raise confidence and reduce false positives based on the analysis of all the different contexts. And it's important to understand that even requests that show high scores for the indicators determined in phase one, that those requests actually can be turned into benign requests based on the combined decision looking at the context in phase two. And on the other side, also something that only received a very low confidence indication based on maybe a single indicator in phase one, that looking at the different contexts, and for example, the fact that this user already did suspicious stuff in the past, and that his behavior is completely different from the typical behavior that we see in terms of usage of the website, in terms of the content of specific parameters handed over with a HTTP request. So also something with low suspicions from phase one can lead to a block action and a malicious verdict in phase two. So now let's go back again to our log4j examples, but now let's take specific vulnerability examples, specific payloads for the 3 CVEs that I've explained before in the timeline perspective, and see how they are actually analyzed in our two-phase contextual machine learning engine as part of open-appsec. So here you can see the 3 examples. So the first one, as we also discussed before, that's the one that's based on using the JNDI protocol and connecting to an LDAP server and handing over an exploit code to the LDAP server and so on. And sending this actually to the web server that's to be attacked. In the second example, we see someone doing like a context lookup for the API version field, which is the same field that this context lookup is actually being done for. So this is like causing this loop thing. And this third example is the one with the infinite recursion based on this specific string here, and all targeted for the same web server. So let's now feed them into our contextual machine learning engine. So when the requests arrive at the phase one, then actually the thing that we detected here when log4 shell was released, and even before, was the dollar curly brace as the single only indicator. So it's only 2 characters, you might think, but it's those 2 characters are already good enough to say that this is somewhat suspicious, and this is not normal, and it at least justifies further analysis. And based on this indicator, on this dollar curly brace indicator, the request was then forwarded to the advanced analysis engines. And in the advanced analysis, then all the different contexts were involved as well in the decision making. So here it was determined that this user, for example, already did some suspicious stuff in the past. So he already sent requests to URLs which were not typical, and in the request there was also something suspicious and so on. So this adds up to making the initial assumption even more strong that this might be like a malicious request. The payload score is actually the scoring from phase one. So $curly brace already by itself has a pretty strong indication, because in the typical amount of HTTP requests in what's used commonly, this is not very common to be part of it. And in contradiction, on the opposite, we see this happening and being part a lot of HTTP requests that are actually malicious. And then we also look at the URL score. So we know that this specific URL is quite prone to attacks, and also look at the specific parameter that's used here, and again adjust the confidence level. So based on the full context with all those different perspectives here, the conclusion is that the final score of 5.3 leads to a risk assumption of high, and therefore this attack actually is blocked as it's considered high risk. Note that this is the example for the first and also the second CVE, because in both cases the $curly brace was the actual trigger, which was good enough to have the indicator detector detect the request as somewhat suspicious. And then the advanced analysis engine did the rest and made sure it's not a false positive and determined the block verdict at the end. So in the third CVE example, we have the request here, and in this case there are actually two indicators. One is the $curly brace, and the second one is the two closing curly braces, which we also know from our offline model where we analyze these millions of malicious requests, that they both are having somewhat of an indication of a request being malicious. So the indicator detector says that there is like an initial suspicion on the request, hands it over to the advanced analysis engine, and in the advanced analysis engine, then again the context is being analyzed. So again, the user reputation is not very good. The payload score is already significantly high. That was given from the indicator detector in phase one. And then there's the URL score, where the system already learned based on the past traffic that was observed that this URL is prone to actual attacks, and that this is not normal behavior that we see on this URL in general, and also not on the specific parameters. So based on this, a final score of 5.4 is calculated, with therefore leading to a risk assignment of high. And because it's high risk, the request is actually being blocked. So now let's do a specific demo and check out the Log4Shell attack in a real environment. So in this example, there's an attacker visualized here, and the attacker wants to attack a web server that you can see here, which is running a vulnerable version of Log4j. So what he's doing, he is contacting this web server at the address .0.6, and he sends this header with the Log4Shell exploit, pointing or asking the Log4j module to connect to an LDAP server, which is this one. You can see it visualized here, and this one is actually owned by the attacker. So the attacker calls this web server. This web server then hands over the exploit that the attacker wants to be executed here, hands it first over to the attacker LDAP machine. You can see it here, base 64 encoded in the actual attack string. And if you decode this, you will see that it tries to upload credit card numbers from the web server again back to the attacker machine here. So flow-wise, he sends this request here. Log4j is instructed based on the JNDI to send the malicious base 64 encoded payload here. And this attacker then uses the payload, creates like a jar file and responds with the jar file back to the log4j module here, and then actually it gets executed and uploads the credit card numbers back to the attacker. So now let's see how this actually looks like. So here you can see two videos, two terminal windows, both belong to the attacker. On the bottom you see him firing up his malicious ADAP server. So he has now an ADAP server listening here and also the web server to collect the credit card information. And on the top window you can see him first trying to connect to the web server he wants to attack, and it's reachable. He doesn't get that page, but actually he can reach it under the IP. And then he does the actual exploit, sending this string with JNDI ADAP that we discussed before. So here on the web server, on the ADAP server that he started, you can see that it received the command. It created the Java class file in this case, returned it back to the web server. And also in the end, the web server then uploaded the credit card numbers based on the curl request, which was encoded in this part of the JNDI based exploit that was sent to the web server. So this attack was obviously successful, and with one single curl command he actually managed to get credit card numbers from the targeted web server. Now let's do the very same attack again in a scenario where open-appsec was deployed before with the contextual machine learning engine. So the attacker is again firing up his malicious ADAP server, which also runs the web server to collect the credit card information if the attack is actually successful, and tries again connectivity so he can reach the web server, and then he's firing the actual JNDI based log4shell attack against the target web server. Now the difference is, in this case we can see that the result is a 403 forbidden. So this was now successfully blocked by open-appsec's contextual machine learning engine. So if we have a look at the resulting logs in the open-appsec web UI, then we can see that a certain incident type was assigned here. So the indicators we saw are typically used in Crosssite scripting, also remote execution attacks. So in this case, obviously it was a remote code execution attack trying to upload code to then get credit card numbers from the targeted system. We saw that the matched parameter was actually the X API version header, and there was like a specific sample here, and the one that we sent. And within this we found various indicators. So there's the $credit brace. There's also some more, because of course we also improve our contextual machine learning model, like the offline model over time. So we continue to train it and make it better. But even when the initial CVEs came out, the $credit brace was good enough already to say that this is actually an indication of an attack, and forward it to stage 2. So meanwhile, today we have additional indicators, of course, and made it even better. So there's like a base 64 indicator and some like a collection of Java related indicators, like Java 1. This contains, for example, the string JNDI as an additional indicator to make it even more accurate. But all of this was not necessary at all to have preemptive protection against all of those log4j attacks, even before they were known and announced and CVEs have been released. So, and then based on the outcome scoring calculation, so you don't see the scores represented here actually, but the result was that the severity was assigned as critical, confidence level very high, and therefore this request was actually prevented. Let's have a look now at another example, which is Crosssite scripting, and not just look at the log4j. So just show you that it can do something more as well. And I said in the beginning that the engine is able to prevent like 0 days, but also all the including stuff based on the typical always top 10 attacks, but also other stuff. So cross-site scripting is a very classical attack. It's a common attack vector which works by injecting malicious code into vulnerable web applications and can result in account compromise, malware activation, page content being modified to mislead users into actually surrender information to the website. It can reveal session cookies and do much more stuff. So in the end, like a successful XSS attack can have devastating consequences for businesses and as well for the relationship of those businesses with its clients. So in order to do some of those attacks and look into this further, we can have a look at the so-called hacker's cheat sheet, which is available at the source that you find below and just lists some examples of cross-site scripting attacks. So in this, for example, we found an attack where an HTML tag table background here is used, and then there is like JavaScript, alert, XSS being added here to create a pop-up when this is loaded that just shows XSS to demo how XSS attacks can be done. So if we look at common solutions today, so many WAF solutions have signatures to identify cross-site scripting. One of them is mod security, which is a very common open source WAF solution, which is again implemented by many other vendors that offer their own WAF solutions or services that are basically based on mod security technology. And within mod security as the actual WAF engine, let's say, there is the so-called common rule set from OWASP that contains all kinds of signatures against all kinds of typical attacks. And in those signatures, we also find a list of signatures for cross-site scripting. And in this cross-site scripting signature, we find the keyword less than table as the thing that actually is one of the signatures being used to determine if there is actually a cross-site scripting attack. And this specific rule set is tagged as always top 10 and also as critical, meaning a critical rule set typically, of course, you would want to prevent and set your solution to prevent and not just to detect. So this is like just to show you the specific rule set. So there's many different keywords that are typically used in cross-site scripting attacks, and here you can see the table and that it's tagged as OS core rule set and with the severity of critical. So what's the challenge here? If we look at a pretty famous wiki solution used in many enterprises today, which is the Confluence wiki, then there's also a very normal common use case that you, when you create a wiki page, edit wiki pages, that you also have tables on your wiki page, obviously. So, and when you have tables, then in the generated code for representing that page, it's totally normal that there might be also a less than, like the %3c is representing the less than sign here, like having a less than table as part of the actual HTTP request, which submits changes or new pages that you create back to the Confluence wiki server. So this means that at this point, if you just look at the less than table and say this is an attack, you would actually create a false positive and throw away this request, and the user might get angry because he has to, he or she might have to do the work all again. And based on the default settings in like mod security, based on the core rule set, for example, the result would be that if you see this as a false positive, you need to disable the rule set or remove this this less than table string from the signature definition, which again opens the door for successful cross-site scripting attacks because it can be used for cross-site scripting. So just saying like I don't want to look at this anymore and create an exception is insufficient. So how does it look like when we send this request to the contextual machine learning engine of open-appsec for actual analysis? Sorry. So in the phase 1, the indicator detector would detect the less than table, same way as the the mod security with the core rule set, for example, would detect it. And the difference is that we wouldn't say it's actually an attack. We would just say, okay, now we have an indication, a certain indication with a certain score of this potentially being a request, and that this is actually suspicious. So because it's suspicious, we hand it over to the advanced analysis engine. And in this advanced analysis engine, now we start looking at the full context, the full picture. Full picture tells us that the user here, which in the case of the Confluence wiki is like an employee that is just using the Confluence wiki solution maybe within the intranet of his company. So he already did like 20 requests so far and never has shown any suspicious behavior at all. So his reputation from the perspective of the advanced analysis engine is very good. The actual payload score is like somewhat medium, so there is a certain likelihood of this being an attack, but this alone is not good enough to say this is actually an attack. Then we also know that on the Confluence wiki URL, it's pretty common to have this less than table indicator. So that again reduces the initial confidence level of this actually being an attack. And we know it isn't an attack. So that's exactly what it should do. And also we know that in the specific parameter of the request, also the less than table has been seen before, so it's not a strong indication that this is like a malicious thing because of based on baselining. At least sometimes before we've seen this here, and it seems to be okay. So and based on all those different contexts, then doing a final scoring, we get to a final score of 2.2, which means a risk categorization of low, and means that the contextual machine learning engine and open-appsec actually will pass this request and not block it, which would have caused a false positive, which would be the case in traditional static signature approaches. So having seen this, the question might come up, so what now about static signatures? What's the value these can still provide? Are they still providing any value? So static signatures still provide additional value, and they have some unique features that you typically don't get from machine learning. So for example, the good thing about signatures is they can give you like intelligence information for specific attacks. So a signature can have like a description that says this signature is specifically for this CVE. For the CVE has a CVSS score, they can have a name, a description, a classification, and so on. So it's good and easy to assign intelligence information to signatures, but that also is the problem because that already like suggests that a signature, as you can assign it to a specific CVE, that already means it's very specific, and you need like a CVE in a way, or you need something known to create a signature for that kind of attack or exploit to even create it. So it's good and bad at the same time, let's say. Also, then as a result, it allows you to search for, if you have signatures in place for a specific new CVE number, when you hear about this maybe in the news. So with machine learning, this is not possible, but also not required, because when you have this contextual machine learning, then there doesn't even need to be a CVE number that it actually already is able to prevent against this. So you cannot check for the CVE number if you have protection, but still you would be protected, which is of course even more important than only knowing later that you are now protected by signature, but having had a vulnerability even before. And then there's, of course, some additional security detection or prevention capabilities. So there's still a chance that you have a signature that is not that detects something that's not covered by the machine learning. Or also there's cases where maybe you get notified about new attacks, and someone gives you like intelligence on how they work and suggests like a signature or something that you want to have in your system. So for this in open-appsec, we also allow you to have snort signatures in place. So you can just enhance, in addition to what we do with all the machine learning, if you have specific signatures you want to add for some reason and you definitely want to block traffic based on some specific signatures, you can just add them as not signatures and have them enforced as well. But also, like when you use signatures, be aware that even if they might get you like some more preventions in some specific cases, also at the same time you enhance the risk of getting false positives. And last but not least, of course, in general, signatures are the result of doing security research, and that by itself is obviously doing very good for the community and the InfoSec community as a whole, and provides strong value and in order to make systems more secure. So after having looked at all the enforcement side and the Log4j attack series and how the two-stage or two-phase engine is working and so on, let's have a quick look now also at the management options, if you might wonder how you can actually like handle all of this. So for the actual configuration management, you have two options. So either you can do it completely declaratively. That means in terms of if you work in Kubernetes, for example, you can just create YAMLs, respectively, custom resources to define like the policies and practices and log configuration and so on for open-appsec running in your Kubernetes clusters. If you work with Docker or just deploy it as an add-on to, for example, an Nginx on Linux, then you can just have a local configuration file, and so it fully allows you to work with GitOps CD pipelines in your specific case. Logging is done to std out, or you can log also via syslog, and we will also soon introduce specific integration with Prometheus and Grafana, for example, for monitoring and logging and so on. Alternatively to doing everything in a declarative way, there is the very user-friendly way of having a web UI to manage your open-appsec deployment, to do the monitoring, to do the configuration. It's a SaaS service that we provide. It's also available for the community edition of open-appsec. So it's easy to use. It's central management, so that means it also allows you to manage multiple open-appsec deployments. Let's assume you have some clusters locally in the cloud and also some containerized versions running on Docker, and also several like regular Linux servers based on Nginx or maybe based on Kong that you want to protect. So all of this can be easily managed from the central UI, and also you see the status. I can monitor the status for your agents, and the logs can be stored in the cloud SaaS service, and you have like log analysis tools and visualizations and so on. And there's also Terraform and GraphQL APIs available to automate the usage of this. And if you think, okay, I need like the DevOps way, but I also want like a nice web UI to see what I have currently configured and monitor stuff and so on, then we also got you covered on that perspective, in that we allow you to do a best of both worlds approach. This means you do the actual management based on declarative configuration, but you can also combine it then with the web UI option, so that in the web UI you can see what you configured locally in a declarative way, maybe in your Git repo with all the pipeline stuff and so on, fully DevOps style. But you still see it then from central management, and also you can monitor your agent deployments from the central management, and you still get the logging centralized and have the event analysis capabilities and dashboards. So that's to combine best of both worlds for management. With regards to pricing, as I mentioned before, there's the totally free open source community edition that you can use, that even includes the web UI as well, and all of them, as I said before, are based on the exact same machine learning, contextual machine learning engine with the two phases that you've seen explained here, and provide the exact same preemptive security enforcement. And in addition, then we have like a premium edition and an enterprise edition that provides some additional capabilities. You can check our website for details on this. The most important thing is that this is typically relevant if you need like support, like a support plan also from our side to assist you if you have specific issues with configuration or need help for whatever. And yeah, on the bottom, actually, you see there's like, we have like a comparison table on our website, which is www.openappsec.io, and then you can check the different pricing. So finally, some takeaways. So we learned that contextual machine learning can provide real preemptive protection even for 0 days based on the contextual two-phase machine learning model, and by not relying on signatures at all, but by using just indicators as indications of initial suspicion, and then looking at the full context before finally coming up with a verdict, which is also important to strongly reduce the false positives generated by the solution. So by doing this, by doing it this way, openappsec also solves the trade-off problem that we saw with regards to having too strict versus too loose signatures. And this actually makes it a game changer for web application and API security, as you've seen based on the Log4j vulnerability examples, because as we've seen, if a WAF solution is just relying on signatures and not involving any additional measures or something like machine learning, then it's just insufficient and it can never really provide true 0-day protection at all. And finally, it's important to mention, I think, always that in the end you should have a combination of multiple parallel security layers based on different technologies if you want to have best protection and also threat intelligence. So that's it. I'm at the end of this video. I hope this was quite useful for you. If you want to learn more about the openappsec project, you can visit our website at www.openappsec.io. You find also our code repository for the open source code in GitHub in the openappsec repository. Then we have playgrounds for you available. So in a playground, you instantaneously can access a Linux environment or a Kubernetes environment, and with some easy steps like deploy openappsec, run an attack, see how it's prevented, add the deployment to our central management, see how everything is represented there. So I really recommend you trying out our playgrounds. And if you have any additional questions, feedback, concerns, whatever, feel free to contact us either via the email address info@openappsec.io, but you can also just go to our website and use the chat functionality, which is available there, to get in touch with us. And on the bottom, you can see, of course, we are also present in all the typical social media networks, from LinkedIn to Twitter and Instagram and so on. So all of those places, including YouTube, you can learn more about us and find updates from us. So feel free to sign up on any of those for our channels. Thanks a lot and stay secure.